100 years ago, give or take, Ernst Rutherford, my age, more or less, he visited Otago and he gave some talks here. And as we can see here on the front page of the Otago Witness here, you see how visiting New Zealand, the land of his birth, Sir Ernst Rutherford, a Cambridge professor of widespread fame, will tell us about his speciality, the anatomy of the atom. Already he has been asked whether the atom really exists. Intelligent people have doubts. And if we look further inside here, we see that actually over what amounts under the heading of a man of science, what amounts to entire page here, it's described in minute detail, his visits here. For instance, he gave a talk at the University of Otago at the physics lecture room on a Friday morning, where the whole seating accommodation was occupied and people had to contend with standing room. We're not quite in that situation today. And when Rutherford he entered the room, he was greeted with enthusiastic applause, and the students would give a haka with great vim in honor of their distinguished visitor. So you too can work on that. So Sir Ernst he raised a hearty laugh at the start of his address by remarking that he was surprised to find what a large number of people were interested in the technical details of the university. And he then went on to say that he was going to give a more or less informal talk, and he would judge by the looks of intelligence in the audience as to how much he was going to say. And likewise, I'm going to give a more or less informal talk, and we'll have to see just about how long I'm going on for. So, welcome to you all on this evening that you called Thursday, but I could sort of call cultural appropriation, because really Thursday gets its name from the Norse Viking hammer-wielding god Thor here, and we see here a drawing of Thor colored in by one of my daughters, where he's wading across a stream, carrying his hammer called Mjølner in his hand, and we see the rainbow called Bifrost going from the worlds of the humans called Midgård to the worlds of the gods called Asgård, and then we have all the gods called Asa. They are riding across this rainbow bridge there. So we call that a preliminary theory for a rainbow. So the word Viking, as featured in the title of my talk, was actually used by the Danes to describe an overseas journey you would go on to win a claim. So you'd go on a Viking, or you'd go Viking, and then you'd become a Viking after have achieved this thing. And on this journey, you could trade or explore or raid. And the meaning for in terms of my lecture is this of exploration, which I've adapted. Somehow, raiding seems to be a bit frowned upon these days. So two words in my title that has no Scandinavian origin whatsoever is atoms and lasers. So atoms comes from the Greek word atomos, so from tomos, to cut, and then an A in front of it to negate it, so something uncuttable. Whereas lasers is actually an acronym which stands for light amplification by stimulated emission of radiation. So it was invented 60 years ago, and at that time it was called a solution in search of a problem. Now atoms, they come in these sort of completely indistinguishable entities, right? For two sodium atoms, they are completely the same, but they are not quite as uncuttable as the name suggests, because we know we have a nucleus that's surrounded by some cloud of electrons. And even the nucleus also can be divided into neutrons and protons. Okay, but for the purpose of my talk, we can actually, for the most part, just consider them as uncuttable, but they will have some kind of quantized structure, and the simplest we can think of is sort of like two levels. So we can imagine an atom being in a lower quantum state here, or it could be in an excited state, in a different state, right? And that's something completely quantum. It can be in what we call a superposition state. So that's something non-classical, something completely quantum mechanical, where the atom in some sense it hasn't decided whether it's up or down. But if we ask it, if we make a measurement on it, it has to commit, it has to say I'm up, I'm down. But until that point, even the atom doesn't know whether it's up or down. Okay, so for lasers, we need a gain medium, and then we need to pump some energy into it. And this is actually what we have over here, what I've set up here. So you see the glowing here is because I saw that there's a discharge, there's some electrical cables going in. So this is my gain medium here. Then around this gain medium, I need two mirrors. So we can actually see the mirrors here. So you have one mirror here and another mirror here. And what happens now is that I'm building up a standing wave of light. So light, you have photons, and they're going to bounce back and forth, and they're going to just grow in amplitude inside here. And now, if one of these mirrors is sort of like partially transmitting, then you can see how I get a spot coming out here. So this is, you see a laser beam here coming out. And we can use this laser to manipulate atoms with. So for instance, if I have an atom in my down state here, I can use the laser to promote it to the up state, or I can even use this laser to put it in to this superposition state. And also what's going to be important for my talk here is that we can also use to mechanically manipulate atoms, so we can move them around in space using the laser. Curiously, if I take a black piece of cardboard and put at this end of the laser, it's gonna stop lasing, right? So you look at the red dot over there, and I'm gonna put in a black piece of cardboard here, and you see how the red dot over there went away. And now I take it out again, and the red dot appears. So this is, of course, now I'm preventing light from being able to bounce back and forth between the mirrors, so therefore the laser action stops. And once I take it out again, we see how the spot appears. Okay, so my Viking is really a story about being curious about the clockworks of nature. And when I say curious, it's not just about discovering that the hands of the clock goes around, but also somehow figuring out why they're going around. And here it says, leg godt in Danish, which means play well. And if you lose some of these letters, as you see here, and contract it, you see how it says Lego, right? So this is where the name Lego derives from. And here we see the instruction manual for one of the kits I had when I was a child. And you see how these train wagons, they're interlinked via small permanent magnets, blue and red, right? So if I have a wagon with a red magnet here, it'll stick together with a blue magnet, and this is how it links together. But of course, if you're 5 years old, you can't help yourself trying what you're not allowed to do and try a red against a red, which then pushes this thing away. And then you think, okay, I can use this to propel a wagon, right? So maybe you could do something clever, right? You could just connect it with a piece of Lego like this. It doesn't work, and I can say from someone aged 5 years old. No, that didn't work. But what actually worked was I was given this little motor here, which I could build into my train engine. And when you send a current through this motor, it would then go in one direction. But also exploring here, if I now took this plug here and I changed the polarity, the wagon would, this motor would go in the opposite direction. Or as I said to myself at the time, so this motor is antisymmetric with respect to interchanging the polarity of the plug. I also got some light bricks, I called them. So these were kind of like, you see here, a small bulb, right? And on the back, they'd fit the same kind of like plug as my engine, so you could plug it in, and then you'd get light out of it. But if you took this light block and you flipped around the polarity, you just get the same thing again. So what I said to myself, aha, this light brick here is symmetric with respect to interchanging the polarity of the plug. Great. So Niels, 5 years, he was investigating, bouncing Lego wagons against one another. So you have two bouncing together here. And me here at 50 is more now considering bouncing clouds of ultra-cold atoms together. So here we see some two clouds of atoms. We're going to get into more detail how it comes about later in the talk, but our work in this thing has been documented in this series of papers in Nature Communication. Right, so the brief for this talk was somehow to give an account for my academic journey to where I am today. And you'd find it to be a natural starting point with where I started at school. But I actually would first go back in time and actually acknowledge what I think is perhaps the most important thing to somehow succeed academically. And this is read a book for your children, so that you can take home this message. And here we see my mom reading for me and my sisters, as Richard said. She was a school teacher. And also give your kids some love. There's my dad. He was actually not a teacher. He would have been a very good one. He was very good at explaining stuff if you have problems in math and stuff like this. So this is actually before I actually started what you might consider an academic career. But I think it's very important that you read books for your kids from a very early age. Okay, so I started primary school in 1980 here. And around 1987, we would have physics at high school, not at high school, but at primary school. And we'd learn about these Danish heroes of physics. So the hipster here on the left is Tycho Brahe, whose observation led Kepler to formulate his planetary motion laws, and eventually, of course, Newton to formulate his laws. We also had Ole Rømer, who's the first to measure the speed of light, or as he called it, the hesitation of light. And then finally we have Hans Christian Ørsted, who 200 years ago discovered that if you take a piece of wire and you run a current through it and you have a compass needle, that it'll make it deflect. And that's actually the physics that's behind my electric motor in the train set. And of course, probably without electromagnetism, it would also be a very dark room in here today. So physics really, along with woodwork, these were my two favorite subjects, really appealed to me. And one thing with physics was like, so now here I have a Danish stone axe, and it's probably like 5,000 years old. So my granddad would have found it in his field, right? And we can sort of agree on what's going to happen if I let go of this stone axe. Well, it's going to hit the floor, right? And also, the person who in the Stone Age fashioned this thing would probably also have been able to come up with this prediction. But what makes physics so fascinating is that we can actually put a number to when does this stone axe hit the ground. And this is sort of like what really fascinated me about it, this mathematical description of the world and this power of being able to predict how things are going to evolve with time. So then I went to what we call gymnasium in Denmark, but that's the same as high school here, and we would learn about Bohr's theory for the atom. And in '63, they asked the Danish population, so how much do you value science on a scale from 1 to 35? And they said 35, and they took Niels Bohr and they put him on this stamp to the value of 35. So it's clear like we really appreciate it, and you can also see from these previous heroes there. I also had the privilege of going to a physics summer school at Sorø Academy, and then finally I graduated, and this is kind of the one regalia you get in Denmark. You get this cap there when you're a student. I also had some really good teachers there. And then I had a gap year where I was first enlisted, and then also spent some time on something called Rødding Folkehøjskole. And this Folkehøjskole is a folk high school, is a special Danish thing. It's kind of like a boarding school for grown-ups where you can sort of pick cultural subjects such as history or drawing or painting and music, right? So this shows sort of like it shows a watercolor I made and also a piece of music I composed, and I'm going to take both of them to my grave. But still, I thought I'd just play a little piece of music for you that sort of like, means something to me. And as you can see from this quote by Kenyon there, I'm not the only one who sort of like appreciates this particular piece by Bach. And then after this gap year, I was ready to do physics. So let's try to now take the trip here from Castle 1 and to the other side of the globe, right? So we are really almost diametrically on the other side of the globe. So here we sort of like see Scandinavia, right? So we have the Kingdom of Denmark here. We have Norway here. Used to be part of the Kingdom of Denmark. We lost it because we took the wrong side on the Napoleon Wars. Faroe Islands, still part of the kingdom. Iceland left within the last 100 years. Greenland, still part of the kingdom. And here we have an interesting place because that's a nice sailing distance if you have these long boats to go on some cultural exchange. But I digress. So I then started studying physics at Aarhus, and I actually must admit that as an undergraduate, I hated it. But it actually got better when I went into postgraduate studies, and under the blue dot there is where the parking lot is, and under that there was a storage ring where I did some projects on both on synchrotron radiation but also on laser cooling of ions in storage rings. And due to that I was sent to these accelerator schools at CERN. So you can see the local one we had here had a circumference of 40 meters. But then I went to CERN and did accelerator schools there, and you can see you have Geneva here, Lac Le Mans, you have also Mont Blanc, and I actually was so fortunate to climb it while my knee was still okay. And that has a circumference of 27 kilometers. So that's really an impressive and also very inspiring thing to see, because when you stand in this tunnel you can hardly see it curve, and also the detectors are just phenomenally large. So you see, I think it's the one called L3 here, and you can see by the size of this man how big it is. So maybe this is what inspired me to sort of build a collider here at Otago. This is the one we have in the physics department, and also for size we have a Lego man here. But before I could build this thing, I somehow needed a PhD. And I got this in Aarhus doing ion trapping with Michael Drewsen, and you see us here on the cover of the local university newspaper. It's called Information and Debat, and that's translated into Information and Debate. And yes, it is a university newspaper. And you see, here we have sort of like a tertiary education day where there are some high school students in, and I'm adjusting the electrodes or the voltage on some electrodes inside of an ion trap inside a vacuum chamber there. And this is an ion trap I built together with my friend Christian Mølhave, who's doing the same job here on the side. Right, so now it's the point where I'm going to tell a joke called 3 magnesium atoms walk into a bar. So here we have 3 magnesium atoms, and how do I know they're magnesium atoms? Well, I can sort of see they have 12 electrons, and if I look at the nucleus, they have 12 protons and they have 12 neutrons inside there. So yes, that's a magnesium 24 atom, and if I now add 1 neutron and 2 neutrons to the other 2 here, I have the 3 isotopes, 24, 25, and 26. And they are neutral atoms now, and we want to have them inside an ion trap, so you need to ionize them. And one way of doing it is bombarding them with electrons. So I can bombard them with electrons, but the problem is this is kind of completely indiscriminate. It's just you have no selectivity. You don't know what you're gonna ionize. So my supervisor, Michael there, he had this great idea that you could use light to selectively ionize these atoms here. So if you, for instance, use blue light, you might talk to the 25 magnesium atoms and ionize those. And if you use the more purple color, you then interact with the 24 isotope and ionize this thing. So that was a very clever idea which we wanted to try out in practice. So 3 magnesium atoms walk into a bar. The first one says, "Holy moly, I think I just lost an electron, I'm ionized." The other 2 says, "Are you sure?" "Yes, I'm positive." And the fact that now this is positive is such that I can use this a configuration of electrodes to trap now these charged particles here in the center. And you might ask, what happens if I put more in there at a time? And we'll get to that in a short while. Because first we need to see if this photonization works. So I have green light, but this photonization needs UV light. So what I did as part of my PhD was making green light violet. And what you can do, the way what you can do is take a small crystal, which is called a nonlinear crystal, and then build a resonator around it. So not kind of like unlike what I have around my laser here. And then you shine in green light through this mirror here, and that bounces off a mirror, bouncing off a mirror, bouncing off a mirror. And then it builds up power inside here. So you get a very large power, and then this crystal will start emitting ultraviolet light, and we could then try if we could use this light to ionize these atoms with. Right, so this is actually a photo of the resonator I built, and you can actually see the laser beams tracing out in there because the intensity is so high. And the funny thing is, of course, that even though you have a very high intercavity intensity, you can stick your hand in here, you're not going to burn yourself because immediately this power build-up stops. Okay, so let's see if we can trap some ions. So this is just the top view of our vacuum chamber here. I have an oven that I heat here with magnesium, and then you get an atomic beam, and then you shine in this ultraviolet laser light. Okay, so can it ionize magnesium atoms? And what you start is, of course, things are running at the end of the afternoon, and you start tweaking knobs and see if do you see anything. And the way we look at it is with a camera, and once you get ions, they're going to get trapped and they're going to light up because you drive it with some laser light. So after 10 minutes, you sort of get the question, so how many atoms ions have you trapped? And he says, well, we only just got started, right? After 1 hour, have you seen any signs of any ions? So, no, it's sort of been a bit tedious. It sort of fell out of lock, the laser, and we had to realign stuff. So where are the ions? And at that point, you sort of say, well, I don't know how to explain this to you, but let me try. Try to spell cat like in catastrophe. Say, what? Just humor me, just indulge me. Try to spell cat like in catastrophe. Okay, C-A-T. Okay, very well. Now try to spell dog like in dogmatic. Okay, D-O-G. Okay, now try to spell fog like in ions. But there is no fog in ions. Exactly, and this is what I've been trying to tell you all the time. Okay, but actually, and this part is actually true, then he said, okay, Niels, I'll buy you a beer for every ion we trap, and then you just sort of hit the magic frequency, and it just came pouring in with ions. So every time you saw we meet at a conference, you sort of say, okay, you now owe me 2,945 beers or something like this. This of course also it kind of answers the question about what happens if you have more ions in there, because if you look at the rim there, it's kind of like it has some structure to it, right? So here we have a roughly 3,000 ions. So if you have more, you get these beautiful macroscopic Coulomb crystals. You can see how the charged particles sits in these patterns there, and they are then laser cooled inside this trap. So a baby like this would be like 1 millimeter long. There's also a very beautiful example here where you can see it's a two-component where we both have calcium and magnesium, and you can see individual magnesium atoms sitting inside this calcium Coulomb crystal. And it was something that really, really blew my mind at the time, that you can use this photoionization to trap a single ion, right? So a single atomic particle, and then take a picture of it, looking at it in real time. So this is a single magnesium ion sitting there. You're driving a single electron in this ion, and then you can sort of see it. I think it's just, it continues to blow my mind. And why is this useful? Well, if I have a single ion like this, and it has all these internal quantum states, say I have 2 of them, I can have it in a ground state, I can have it in an excited state, and I can prepare it in this superposition state. And if I now call one of them 0 and 1, it's kind of like reminiscent to what we have in a computer, what we call bits. And this is actually what then makes up what we call a qubit, and it can be used to construct a quantum computer with. Okay, so as part of my PhD studies, I also got to go to the ICAP 2000 conference in Florence, where I had a really life-changing talk, or heard a life-changing talk, and it was given by Wolfgang Ketterle, and it was on the subject of Bose-Einstein condensates. And it's one of the most sort of impactful talks I've ever heard in my life. So here's me paraphrasing Kenyon on Bach, right? But it was really after this talk, after I collected my jaw from the floor, I turned to my supervisor and said he's going to get the Nobel Prize, which he did the year after. So I was really just blown away about experiencing science at that level. So after my PhD, I did a first postdoc at the Risø National Laboratory, where I continue doing this frequency doubling here for the purpose of doing photodynamic cancer therapy. And after I cured cancer, then not quite, but we did get blue light out, and this is again showed. It was some really magnificent people that were there hanging out with these PhD students. So in terms of that, it was really fun, but I couldn't really let go of these Bose-Einstein condensates. So Kim there, who was assisting Stephen in consuming what's called a tequila slammer, he one day came and he put this job advertisement on my table, and it was a postdoc fellow position at Otago with someone called Andrew Wilson, and I applied and I got it, and I started working with a PhD student called Nick Thomas, and eventually we produced 2 Bose-Einstein condensates in a double well trap. And that was really fun working together with Nick, but we really didn't know what to do with these 2. So in some evening I said, let's just see if we can merge them. And this is what happened when I tried to merge them. So they just smashed into each other, so not really merging, but scattered out these particles. So in some sense, by accident, we invented this magnetic collider for ultra-cold atoms. And you see how these atoms, they go out in this spherical shell there with an isotropic probability. It turns out that depending on the energy, you can get all sorts of patterns, but it was really successful, and we got the cover of Physical Review Letters in 2004 for that. I also worked together with, extended this magnetic collider work with a PhD student called Angela Mellis, who's seen here feeding sellotape to my oldest daughter. I hope you haven't taken any damage from that. And also, this was a time where I met Blair Blakey, who's in the audience tonight. He's actually wearing the very same tie, I see. And you see, we haven't really aged one bit, so this is us at the university's 150th year birthday. So Blair is probably the most generous person I know, right? And you could never wish for a better friend in your corner. And I'm not only saying that because he's the HOD, and I'm going to talk later on. I should also actually pause to actually thank all the PhDs, so starting with Rob Ballack, Pat Langhorne, and also Craig Roger for their support and putting up with me over the years. So thank you. Okay, so after Otago, I then went to the famous Niels Bohr Institute, working in the group of Professor Eugene Polsek here, and you see it says 1920. So that's Society founded about 100 years ago. And inside, behind these walls there, you would have the famous Auditorium A, right? And you see pictures of all my heroes there. You have Ørsted on the wall, you have Rømer on the wall, you also have Bohr on the wall, and you would also see photos of the who's who in quantum mechanics who'd been sitting on these very benches before you. You have Bohr, Dirac, Heisenberg. This is just a zoo of them, right? So of course, any workshop you would try to reenact photos of this sort, but I would say you never really reach that level of caliber of physicist. So at Aarhus, I worked at the Atomic Club. I was sort of the senior guy there. We were 5 of us in total. And what's an atomic clock about? Well, the clever thing is I already told you that if I have a certain sort of atom, speaking sodium or cesium or rubidium, they're all the same. They're completely the same. So that means if I have a cesium atom in Copenhagen and I have one in Dunedin, and they have a transition frequency between 2 states, I can use this to implement a clock that ticks at exactly the same rate, right? So I don't need to pick up the phone to negotiate these things because they are really the same. So they're ticking at the same rate. And one way you can sort of implement a clock protocol is I start with an example of atoms in a ground state here. So here I have 36. Of course, you have many more, but just for the example, humor me and follow along. I have 36 in the lower state here, and then I apply some radiation pulse, which puts them into a quantum mechanical superposition, all of them. And then I wait. And I wait for a while. And I wait for a while. And then I apply a second pulse of radiation. And then I look. Okay, so in this case here, if I looked at the atoms, I would say, okay, probabilistically, most of them are in an up state. So I'd say there are too many up, the clock is too slow, and I use this to then adjust the frequency of the field I'm using here. So therefore, I'll increase the frequency here. However, had I ended up in a situation where most of them would kind of like the probabilistically have been in a down state, I'd say, okay, now there's too many down, the clock is running too fast, so I have to slow down. And in the final cases, of course, if I end up with where I came from, where all of them in an equal superposition, I should sort of say, okay, I shouldn't do anything. But here's the problem with that. It's because if these atoms, they are independent and I interrogate them. So I start here, I ask the first one, are you going to be up or down? And it has to say up. And the next one, I'm going to ask up or down. And it doesn't know what the previous one said, so it's going to just answer with 50% probability, and so forth. So it's kind of like having 50 coins, no, not 50, 36 coins, right? So there's a 50% probability, right? And how many heads are you going to get? I have 36 coins. How many heads? I don't know, you're probably saying. Okay, you have to bet your life on it. I say, okay, 18, you say. That's a very good get. I mean, it's actually the best thing you can do, right? But by far in the most cases, you'd actually get something different. Only in 30% of the cases, you'd get 18 coins up. And the same thing happens with atoms here, and that's sort of like adds some width to my distribution here that limits the accuracy of my clock. So if there was some way there you could somehow squeeze this distribution, you could then build a better atomic clock. And this was what we were working on there. And it was eventually published in this journal called PNAS. Squeezing of quantum projection noise on the cesium clock transition. I'm not going to troll through the paper, but you can sort of see the essence of it. You start out with something that's quite noisy, and then the fluctuations are reduced here. Okay? And the way it works is you create something called entanglement between these atoms. And you can sort of imagine you have two atoms in an equal superposition here, and then you shine light through it and do a joint detection. And this creates something called entanglement between these atoms. And as an example, they could be entangled in a state that if I now ask atom 1, are you going to be up or down? It answers up. Well, then the other one has to answer down. And if I ask the first one, are you going to be down? Well, then the next one has to answer up. But I could also have started with the second one and asked that, are you going to be up and down? And it actually doesn't at that point know whether it's up or down. And it answers down, and then the first one has to answer up. And so forth, up, down, east, west, north, south, right, left. So it's going to be correlated in this way. And this kind of like correlation will persist even if you take these atoms and you take one and put it in Copenhagen and Dunedin. And it's what Einstein referred to as a spooky action of distance. So he didn't like this thing. But it is, as far as we know, a thing. And we saw what actually powered this squeezing of the cesium clock transition was sort of like an entanglement between these atoms where when I interrogate them, they are not going to be independent atoms, but they're going to be correlated. They conspire in a way to actually have a narrower distribution, and therefore a more precise clock. So after that, I had a stint as a staff scientist at the Danish Institute for Metrology, where I did laser spectroscopy, so something called cavity ring-down spectroscopy, and I'm not going to take you through this complicated setup that I built, but in a nutshell, it was kind of like measuring two isotopologues of carbon dioxide, and if you can measure this very accurately, if you have a sample of honey or something, you can say something about its origin. But then I sort of got this offer of going to Otago in November 2010, and I thought, okay, I can't turn that down. And I'm just going to skip some of the stuff we are investigating and just talk about these steerable tweezers, which someone previously said they had no idea what they're about. I hope I'm going to inform them on that, and also how we can now, rather than having this magnetic collider, build an optical collider for ultra-cold atoms. So back to here, and at the time The slogan was your place in the world, and it was something that really resonated with me. And I remember Harleen spoke to the effect that she had come from America and made it her place in the world. And it was something I also thought, okay, this actually, I feel the same thing, that you can move here and make it your place. And here we have a stamp of Rutherford to the value of 1 cent. And he also famously said, all science is either physics or stamp collecting, so let's put him on a stamp to the value of 1 cent. But it sort of summarizes very well what we are looking at. So we have a scatterer here, and then we have some incoming particles, and then they're going to bounce off, and we're then going to ask what is the probability of going out in a certain direction here. And this is the apparatus we use to investigate it with. So this is this optical collider and these steerable optical tweezers, and the red devices you see there, they're what's called acousto-optic deflectors, which you can take a laser beam like this, and then you can steer it around in space. So we sort of use this the property of laser light, that it can be used to spatially manipulate atoms. And for what I'm going to tell you about now, the only thing you actually need to know is atoms would like to sit where the intensity is highest for the kind of laser beam I'm using. So here I have 2 laser beams that I cross. The intensity is highest at the yellow spot, so this is where the atoms would like to sit, and I can trap them at this point. So if I devise a way where I can move one of the laser beams, well, then I can move around my atoms as well. And if I devise a way where I can split this, well, maybe the atoms will follow suit. And this is indeed what they do. So this is actually real data now. It's an ultra-cold cloud of rubidium-87 here, being split by laser beams taken out here. And then to perform a collision, we then rammed it back again, and you see how the atoms scatter out in a beautiful pattern here. And we can then sort of like do a polar plot of the angular scattering here, and you see it has really some structure to it. And let's try to see if we can round up the usual suspects. So in quantum mechanics, this is how the usual suspects for something like this looks like. So this is what we had, and I got this angular distribution here. For unknown reasons, we need to take the square root of this, so we get something like this. And you see how it just fits there. And what we looked at previously was this isotropic scattering, and that would fit just up there. So that's kind of like interesting that these rubidium atoms picks these patterns there. It looks a bit like the Batman logo, I think. But really, it's not so much the DC universe, it's more the Marvel universe we are in, because they're actually more like Spider-Man. So this is how they actually behave. And you see how they group in 2 varieties here. So on one side I have symmetrics, and on the other side I have antisymmetrics. So the symmetric one is like my light brick here, and the antisymmetric is like my train engine. So if I swap around here, you see I go from red to blue, so that's antisymmetric. If I swap over here, I go from red to red, so that's symmetric. And the reason why rubidium-87 picks one of the symmetric, or any combination of it, is that we're dealing with indistinguishable bosonic particles. On the other side here is what I would get if I had indistinguishable fermions. And what makes rubidium a boson is because I have an even number of particles. So you can sort of count up the number of protons, you can count up the number of neutrons and electrons, and you get an even number. If I did the same thing with potassium-40, I would end up with an odd number of particles. So that means if I now do the same experiments, so these are now potassium-40 atoms, and I smash them into each other, I'm going to get something over here on the antisymmetric side. So in fact, I'm going to get this thing up here, which is called a p-wave. And now something really curious happens, because on the bosonic side, there is some kind of like energy dependence when I go up in the hierarchy here. So if I lower the energy, I'll end up with what's called this S-wave here. If I do the same thing on the fermionic side, there is no S-wave. So I end up in the situation, if I collide 2 clouds of atoms, they're just going to pass through each other. They're not going to scatter, simply because they're indistinguishable fermions. Right? So it's kind of like having, in terms of my Lego there, if I'd had 2 train wagons that look the same, they just pass right through each other. But if I had now then colored one of them blue, I'll just wreak havoc here, right? And this is what we see by painting one of the clouds in a different color. You get an enormous amount of scattering. And here painting actually means putting them in a quantum state that makes them distinguishable to the other kinds of particles. But both cases here are potassium-40, so that's also really remarkable. So this antisymmetry here goes in hand with something called Pauli exclusion. So as I said, potassium 40 is a fermion. So if I put it inside a quantum mechanical system, so I have these quantized energy levels, exclusion means I can only put one of them in each state, right? So this is what represented here on the left-hand side. And you kind of like know anyone who's done some fundamental chemistry. We already saw an atom like this. You have this electron shell structure around it. And the reason why I get this shell structure is because the electron is a fermionic particle, so I can only put one in each state. So this is why it distributes like this. So what we did recently was we took some fermions and we put it inside a trap, and we filled up all these levels from below here. So kind of like have a boss, and all the seeds are taken there, at least in the front end of it. And then we took a laser and we shone light on these atoms there, which meant that they're going to scatter light and we can take a picture of the atoms. And it looks something like this. And then we took the same number of atoms, but we make some hole in this distribution there. And then we did the same thing, and you saw how you scattered more light out. So that's interesting, like you have the same number of atoms, but you get more light scattering when you have these holes. And this is because this process of light scattering becomes Pauli blocked, because any scattering event from an atom means that I have to recoil as an atom when I redistribute my photon in a different direction. And if all the seeds in the boss are taken, the lower ones, they have nowhere to go. So therefore, you see this difference between scattering, whether you're what's called quantum degenerate or whether you have these holes in your distribution. And if you had $15, you could buy this issue of Science magazine in which it was reported. And if you had $2.50 New Zealand dollars, you could also buy the Otago Daily Times and read about it. And here I would really like also to say a big thank you to Amita Depp, who's been my wingman for the past 12 years. Thank you, Amita, for your friendship. It's really been a great run. But I digress. We were onto this thing with the dream of bosons, right? And unlike fermions, bosons, they are not antisocial. So in fact, the more the merrier in a quantum state. They're going to pile up there. And this is actually this Bose-Einstein condensate I was talking about initially. I came here to explore. So now we know the name of the game. I can have a cloud of atom in my optical tweezers here. And I can use these tweezers now, split these laser beams apart, and I can make 4 clouds of atoms. So inside my vacuum system is going to look something like this. If I zoom in, see I have a horizontal beam, and then I have 4 beams going. So at the intersections, I would have then ultra-cold clouds sitting. Now I have this configuration. I'm going to lower the power of the blue laser beam here. So that means that the hottest atoms, they actually have a chance to escape. So that leads to something called evaporative cooling. So the remaining one, they're going to rethermalize, so they're going to get colder. And in this way, you can go from these Gaussian thermal blobs there, if you take pictures of them, and to these very, very spiky distributions that are a signature of Bose-Einstein condensates. And in this case, we have 4 of them here. Okay, so let's now try to take 2 of them and let's try to gently merge them together. So now something interesting is going to happen. So if I'd taken what we call a double slit here and taken my laser beam and I send it through such that I saw it divided up into 2 and I recombine it, you'll see something called interference. So you're going to see a stripy pattern. And the same thing is going to happen here for these atoms. They're going to develop this stripy pattern once I put them together. And this is like they coined the term an atom laser. So in some sense, it's the atomic equivalent of a laser. So now we've kind of gone full circle with atoms and lasers. And you can also classically, if you excite 2 water waves, you see how I also get these stripy patterns where they interfere, right? You see there's stripes going out there. So this is really what we also see now with Bose-Einstein condensates. So, but Niels, you had 4 of them. What's going to happen if I merge them together? And that's going to be a story for another evening. Because now I'm almost at the end of my Viking here, or the description of it. So I don't know whether I would call myself a man of science. And if I look at it, it seems like there was a point in time where I could do all this lonely work in the lab myself, and then I ended up now sort of posing next to people who are doing the actual work. And it looks a bit depressing, but then I actually figured out that really I should just move this photo up here, and it looks a lot more optimistic. And it actually, the one thing I really, really appreciate is sort of working with these bright young people. So this has really, really been a privilege if any of you are out there. And I next want to just show a little sort of slideshow of some of the people who came through my labs during the past 12 years or so. And this was my daughter, Dita Sofie, here at age 10, who's like giving the music for it. She has an older sister called Ida Senior, and here they are with a little video.
Hi, Dad, we love you.
And I love you too, girls. And you've really been an inspiration for me during this time here. Your skill and your determination. So. It's really been good having you around. And then I would also really sincerely and finally, but for us most importantly, thank Anne-Katrine for your support over the years, right? Thank you all for reading books for our daughters, and thank you for giving your love to all of us. So here we are. I've talked about atoms, I talked about lasers and gentlemen, and also you see there would actually be a lot of women in my group, and also how we could use lasers to manipulate atoms with and construct this atomic collider for atoms. And I hope when leaving now there's going to be no doubts about the existence of the atoms, right?